In the last video on this channel, I've talked about MIDI files and how they work. One major takeaway from it was that MIDI does not contain any audio. So, how can we play back a MIDI file with instruments like this? For that, we're going to use Soundfonts. This video is heavily based on a particular document, the Soundfont Specification. I'll link it in the video description as it's invaluable if you plan to read data from Soundfonts yourself. I recommend you use it alongside the video, if you're really interested in implementing stuff. Soundfonts contain sample data for different instruments, which if we read them out, we can do with whatever we want. In my case, of course, I wanted to use these samples to properly play back MIDI tracks. But Soundfonts contain a little bit more than just sample data. They also contain a bunch of metadata and information about how the samples should be played back. This information is stored in what the specification calls generators and modulators. Generators tell us more about how the sample should be played back, and modulators allow us to alter how samples are played back in real time, through various sources such as MIDI messages. In this video, we're going to focus on how to parse all data from Soundfonts and how generators are used. We're mostly going to ignore modulators, mainly because I have yet to implement that feature myself, and therefore I don't know enough about the pitfalls you may encounter when implementing it. So, a Soundfont is just a collection of metadata, sample data, generators, and modulators. The whole thing is stored as binary data in a file on your computer, so we're going to take a look at how this data is structured. If you've watched the video about the MIDI file format, you may remember that MIDI files are separated into chunks. The same is true for Soundfonts. Each chunk has a label, a size, and then the actual data of the chunk. Here, the label is just an ASCII encoded string spelling out test. The size of our data is 4, and that data contains 4 bytes, AA, BB, CC, and DD. But it could contain anything else, of course. You may have noticed, but the size is stored in little endian this time. Pretty much all data in the Soundfont uses this byte ordering. There are two differences compared to the chunks we used in the MIDI format. First, a few chunks will be preceded by an additional 4-byte string, which for simplicity I'm just going to call a pre-label. You'll see what I mean in just a moment. Second, chunks can be subchunks of other chunks. In those cases, a chunk's data actually contains an array of subchunks. Let's look at the general structure of a Soundfont to make sense of all this. The top level chunk of a Soundfont is preceded by a pre-label spelling RIFF. This indicates a sort of header for our entire file which contains all the other chunks. Why RIFF? Because the whole structure of chunks is called the Resource Interchange File Format. It's basically a common structure used by different file formats, the Soundfont included. And thus they decided to pre-label our main chunk with RIFF. Like all chunks, the first one contains a label, which is always SFBK. The data contains 3 additional chunks, each preceded by a 4-byte pre-label spelling list. And we can differentiate these chunks by their label. Inside of them, we find more subchunks that contain the actual data of the Soundfont. As you can see, there are quite a lot of them, so let's go through each chunk one by one. The first chunk is the info chunk. This one is a lot simpler than it looks. It just contains a bunch of subchunks, each containing some metadata. The data of most of these is just a string. These strings are always null-terminated strings of up to 256 bytes. To keep the data aligned properly, if the number of bytes including the null terminator is uneven, then a second null terminator byte may be used as padding. The IFIL chunk contains the Soundfont's version. It's stored using 4 bytes, where each pair of 2 bytes represents the major and minor version respectively. The ISNG chunk contains a string with the name of the sound engine used, but we don't really care about this. The INAM chunk contains a string with the name of the sound bank compatible with the Soundfont. For example, if your Soundfont supports general MIDI, which may be used to define instruments by a MIDI file, then this string may spell general MIDI. But of course it could use any other name. The iROM chunk contains a string with a ROM name. If I understand correctly, a separate ROM may be used for some samples. If so, this name can be used to identify that ROM. But again, we don't really care about this chunk. The IVER chunk, like the IFIL chunk, contains a major and minor version, except this one is for the ROM's version rather than the Soundfonts version. The ICRD chunk contains a string for the creation date. The IENG chunk stores a string with the name of the sound engineers, so basically the authors of the sound font. The IPRD chunk stores a string with the product name. The ICOP chunk stores a string with the copyright information. The ICMT chunk contains a string with any custom comment. And finally, the ISFT chunk contains a string with the name of the software used to create the sound font. So that was a lot of them, but as you can see, it's all just metadata, nothing fancy. Next we have the sdta chunk. This chunk is where we can find the actual sample data. There are two possible subchunks in this chunk, called SMPL and SM24. The SMPL chunk stores 16-bit signed little endian samples. Pretty self-explanatory, it's simply an array of sample points of a waveform. The SM24 chunk, if present, contains an additional 8 bits for each sample point, which allows the sound font to use 24-bit sample data. It works like this. If we only have the SMPL chunk, we simply use its 16-bit samples. However, if we have both the SMPL and SM24 chunks, then we use the 16-bit samples and then OR the additional byte from the SM24 chunk into them. So the bytes from the SM24 chunk make up the least significant byte of our sample points. Note that all samples are stored in one big array here. Well, or two arrays if the SM24 chunk is present. But that means that all sample data for all instrument sounds is just stored as one big array of bytes. Other chunks, as well as generators, will tell us where in this big array we can find particular samples for an instrument. And that's all there is to the sdta chunk. It just contains our sample data. Now we get to the final list pre-label chunk, which is the pdta chunk. The Soundfont specification also calls this one the Hydra chunk, because it contains 9 subchunks. Get it? Because a Hydra is a 9-headed beast? We're gonna go through each of these chunks in the same order as the specification does, so you can easily find each section if you're using it alongside this video. The first kind of subchunk we might find is the PHDR or preset header chunk. This one gives us information about each preset found in the sound font. For our purposes, we're going to assume that our sound font is compatible with general MIDI, which means each preset corresponds to a MIDI program. So for example, the preset with ID 0 would be grand piano. Preset ID 56 would be a trumpet, and so on. Note, however, that when people talk about general MIDI instruments, they start at 1 for grand piano, so they're all offset by 1. The data of the PHDR chunk is simply an array of preset header data. And here is what a preset header may look like. It begins with a 20-byte string with the name of our preset. Then follow two 2-byte values, one for the preset ID we just talked about, and one for the bank ID. This combination of IDs is used to differentiate our presets later. Next comes another 2-byte value, which is a preset bag index. In a moment we'll talk about what bags are, but for now just remember that this index tells us where the first bag of this preset is located. Finally, we have 3 4-byte values for the library, genre, and morphology of our preset. According to the specification, these are reserved for future use, so for our purposes they don't matter. To reiterate, the PHDR subchunk simply stores an array containing multiple instances of the structure we just talked about. An interesting thing to note is that the last entry will always have the exact preset name EOP. This entry is just used to indicate the end of the array. Next are the subchunks called PBAG and IBAG. We'll talk about these together because they contain exactly the same kind of data, except one is for presets and one is for instruments. The 2 bag chunks just store an array each, where each entry is a bag. And here's what a bag looks like. The first 2 bytes are always the generator index, and the next 2 bytes the modulator index. Now remember how every preset header stored a bag index? This tells us where in the pbag array we can find the first bag for a given preset. The next subchunks are the pmod and imod chunks. And once again, they just store an array each, this time made up of modulator information. Each field in this modulator information structure is just a 2-byte value. The first two store the source and destination of the modulator. The next 2 bytes are a signed integer storing the amount of modulation, and then follows the amount the source impacts the destination as well as a transform enumerator. So what are these used for exactly? Basically, the modulation feature allows us to manipulate some kind of output, which is the destination stored in the structure. This generator is influenced by the specified source. A source could, for example, be a MIDI continuous controller message or event data. A quick note on MIDI CC messages. In the MIDI video I showed a MIDI event called control change. I explained that it corresponds to buttons or knobs being pushed or turned on a device. And while that's technically true, more specifically these controls correspond to different things that are controlled by those buttons and knobs. For example, there's a MIDI CC for volume, one for panning, one for the sustain pedal, and so on. Anyway, the amount values in our structure tell us how much the source influences the destination. But again, I haven't implemented this feature myself, so my knowledge of it is limited, and we're going to ignore it for the most part. Moving on, we have the pgen and igen chunks. These store a big array of all generators for presets and instruments respectively. So what exactly is a generator? A generator is a pair of values. The first is an enum specifying the type of the generator, and the second is a value associated with that type. For example, generator type 52 is the fine-tune generator. Let's say we find an instrument generator with type 52 and an amount of 10. That means the instrument with this generator needs to be pitched up by 10 cents. Depending on the type of generator, the amount can either be signed, unsigned, or a range defined by each of the 2 bytes representing a minimum and maximum amount. Next we have the inst chunk, which contains instrument header information. It simply contains a 20-byte string for the instrument's name, followed by a 2-byte bag index. Once again, this bag index tells us where in the ibag chunk we can find the first bag owned by this particular instrument. We're going to look at what that means in just a moment, so don't worry if it makes no sense right now. Like the phdr chunk, a terminating entry named EOI can be found at the end of the inst chunk's data. Again, this is just used to indicate the end of the array. All that's left is the shdr chunk, containing sample header information. As always, the data is an array of a certain type of data. This one again contains a 20-byte name. But then we have some very interesting data. The start and end position, in sample points, of our sample data. These start and end points correspond directly to indices in our sdta sample data from earlier. Then we also have loop start and loop end data, which tells us at which sample points the sample is looped. Whether or not a sample is actually looped is defined by a specific kind of generator, so not all samples are looped. Then we have the sample rate in hertz, so it just tells us how many sample points make up a second of audio. And next we have the original pitch at which the sample was recorded at. This is represented as a MIDI key number, which if you remember from the MIDI video corresponds to this table here. Moving on, we have the pitch correction value. This one tells us by how many cents we should pitch the sample up or down. And finally, there are 2 values called sample link and sample type. The sample type tells us whether the sample is a mono sample, so it only contains one channel of audio. Or it could indicate that the sample is either the left or the right channel of a stereo sample, and whether it is stored in a separate ROM. If the sample contains the left or right channel's data, then the sample link simply contains the index of the sample header for the other channel. This basically links them together. And just like the phdr and inst chunks, there's a terminal entry in the shdr chunk named EOS. Once again, it just indicates the end of the array. And that's it. That's everything contained within our sound font. The next step is to take this data and actually do something useful with it, and that's where things get a little bit more tricky. Okay, so our goal for this video is primarily to start with some MIDI program ID and generate sample data used for that program's instrument or instruments from the Soundfont. Doing this is not hard, but it's a little bit of a pain. Let me show you what I mean. We start with a preset ID and bank ID. Remember, in our example case, we assume that the preset ID is the same as a general MIDI program ID. And for our bank ID, let's just assume it has a value of 0, which means we're targeting the very first bank in the file. First, we could go through our preset headers, so the phdr chunks data, and find the preset with the specific IDs we're looking for. But how do we get from this preset header to the actual sample data? First, we need to inspect its bags. The first bag of the preset is referenced using the bag index stored inside the preset header. It's simply the index in the pbag chunks array of bags, where we can find our first bag. You may have noticed I keep saying the first bag. Our preset actually has multiple bags, so how do we know how many? Well, for that we need to get the next preset header from our phdr chunk, check its bag index, and then get the difference to the other bag index. Basically, all bags are stored in the same order as our preset headers, and we can use the next preset header's bag index to know where the next bunch of bags begins. With this knowledge, we can easily find the first and the last preset bag. Then we loop through these bags. For every bag, we can now check the generator index to find the first generator of this bag in the pgen chunk. Again, it's only the first. Just like before, we need to now look at the next bag, find its generator index, and use that to determine where the last generator is located. Once we know where the first and last generators are located, we iterate through those as well. And finally, we get to examine each generator. Now, I'm not entirely sure which generators can occur at the preset level, primarily because in practice, I've only ever seen Soundfonts specify a single one, which is the only essential one, generator 41. This is the instrument generator. It always comes last in the generator list, and its value simply tells us where to find the instrument header related to this preset zone inside the inst chunk. If this generator is missing from a preset bag, then it's considered a global preset. That means its generators apply to all other bags of this preset. So again, with the instrument generator, we get the index in the inst chunk where we can find our instrument. Note, however, that as far as I'm aware, many other generators can appear at the preset level. I just haven't seen them there before in the wild. Anyway, with our instrument generator, we can grab the instrument header. And guess what we do now? We repeat all the shenanigans we just went through, but for the instrument rather than the preset. So again, we find all bags of the instrument, except they're in the iBag chunk rather than the pbag chunk. Then we take each bag, find its generators in the iGen chunk. And finally, we end up with each generator at the instrument level. Again, we have to examine these ones one by one to determine how our instrument should be handled. Here we will usually find many different generator types. There are 61 of them in total, so I won't go through every one of them, but instead highlight the most important ones for our purposes. For more, you should take a look at page 30 onward of the specification. The first few generators worth mentioning are address offsets. These simply provide extra offsets to our sample's start and end, as well as the loop start and loop end values we get from the shdr chunk. Talking about the shdr chunk, how do we know which sample header belongs to our instrument? That info comes with generator 53. Its value is the index in our shdr chunk's data, where we can find the sample header data for this instrument. Just like the instrument generator in the preset level, this one always comes last at the instrument level. And if it's missing from a bag, then that bag is considered global. Another common kind of generator is number 43, the key range generator. It specifies a minimum and maximum MIDI key number used for this instrument, and always comes first in the generator list if it is present. Now you may be wondering, why would we have key ranges for instruments? It turns out an instrument can technically use different sampled sounds for different keys. An example of this is the Percussion bank found in Soundfonts. It stores a bunch of percussion instruments, which all come from a single preset. But Using the key range generator, these different instruments are assigned to different keys or notes. So if you play a middle C, it may be associated with a bass drum, and if you play a D next to it, it may be a snare drum or something else. The same goes for key velocity, so how hard a key is pressed. The velocity range can be defined with generator 44, and it can separate instruments by key velocity, although I haven't seen this actually used in a Soundfont myself. Also important is the sample mode generator. This one tells us if and how a sample loops. As you can see here, its value is either 0 for no loop, 1 for a continuous loop, or 3 for a loop that only persists while the key is held down. And there are the coarse tune and fine tune generator I mentioned earlier. These just tell us to shift a sample's pitch by some amount. Finally, there are generators for the volume envelope of the preset or instrument. These tell us how the volume behaves over different states of a key press. You know, attack, decay, sustain, release, you've probably heard of these before. And that's pretty much it. There are more generator types, but these are the most basic ones that you definitely want to support. Now with all these generators, bags, presets, instruments, and so on, you may still be left a little confused. It's all very messy, mainly because of how our data is laid out in such a confusing way. So I wrote this simple script. It's pretty ugly and suboptimal, but all it does is loop through the presets, bags, generators, etc. to find the preset with preset ID 0 and bank ID 0. Adding some print statements at each loop, I got the output you see right here. Let's examine this output because it's the output of a real sound font and see how everything works in action. As you can see, we found a single preset with the desired IDs. This preset is named Piano 1. Inside of it is a single preset bag. This preset bag then contains a single generator, number 41. This tells us where we can find the corresponding instrument header. Grabbing that instrument, which is also named Piano 1, we can see that it has a bunch of instrument bags. Notably, the first bag does not end with generator 53, the sample ID generator, so it's considered a global bag. All of its generators apply to the remaining bags as well. So here the envelope generators, for example, tell us how to handle the volume throughout a key press. And because they are in the global bag, this envelope applies to all other bags. Looking at the remaining bags, we can see that they all begin with the key range generator and end with the sample ID generator. This tells us that there are different samples used for different key ranges. In this case, our piano has samples for different groups of keys. My guess is that this is done to preserve the quality of the piano sound across different keys. If you think about it, a single piano sound that is pitched way down probably sounds like crap. So they have separate sampled recordings for lower keys, slightly higher keys, even higher keys, and so on. And that's what a preset looks like in the real world. First, I should state the obvious. Using 5 nested for loops to grab our instrument samples is terrible, especially if we were to do so in real time to play back music. So obviously our first step after writing a parser is to store the parsed data in a more reasonable format. What I did for my MIDI player is very simple. First I made a data type. Let's call it sampled instrument that contains all important data we get from our bags. This includes the sample start and end points, pitch, envelope, and so on. Every important piece of data read from the preset, instrument, or sample level goes in here, including what we get from generators. When my program reads a sound font, it grabs the data, places it into sampled instrument instances, and then places those in a hash table. The keys used to access items in this table are simply generated from a preset ID, bank ID, as well as key numbers. This makes it super easy to just grab a previously read instrument, and we can reuse them without ever having to look at the Hydra chunk ever again. I'm sure there are better ways to store the data you need, but how you format the data is up to you and your specific use case. Another thing worth talking about is the percussion bank I mentioned before, especially because I didn't explain it yet and didn't even talk about it in the MIDI video. In general MIDI, channel 10, or the channel with index 9 if you start counting at 0, is conventionally the percussion channel. Why is this important? Because in our sound fonts, the bank used for percussion is preserved to be number 128. So if you try and play back a MIDI track on channel 10, make sure you access its presets using this bank ID. That little detail took me forever to figure out. I couldn't make drums work until I randomly stumbled upon this information, so I thought I'd bring it up. Anyway, I hope this video gave you a good enough idea of how Soundfonts work. Of course, what we've talked about in this is just the structure, data, and the use of generators. For more information, refer to the specification. We also didn't talk about how to actually generate audio from the sample data. I'm gonna assume that you know how to do that with your language of choice and libraries available to you. But handling audio in general would be a nice topic for a video, so maybe that'll be something for the future. Anyway, thank you for watching and have a good one.